Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is parallel complex impedances. Our objective is to learn to calculate the total impedance of side-by-side or parallel arrangements of complex impedances. This lecture operates under the presumption the viewer has watched the Series Complex Impedances lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. During the course of the Basic Electronics 1 DC Circuit Analysis playlist, available at the Big Bad Tech channel, recall we had numerous occasions to acquaint ourselves with a DC analysis of parallel arrangements of resistors. This lecture is merely an extension of this much earlier discussion into the realm of AC circuit analysis, incorporating reactive elements like capacitors and inductors. As such, I'm going to skip a lot of the superfluous discussion and get straight to the point. Let us begin. There are two methods used to calculate the total complex impedance of a side-by-side or parallel arrangement of complex impedances. One is a quick and dirty method used exclusively for parallel arrangements of only two complex impedances, and the second is a rather unwieldy calculation used for parallel arrangements of two or more complex impedances. I have a special fondness for the quick and dirty method because of its reliability and practicality, simply because one can ordinarily expect circuit analysis scenarios to involve only two elements. However, there are occasions in which you are presented two or more elements in parallel and need to accomplish the task as quick as possible. For this reason, I'm requesting you familiarize yourself with both methods. Luckily, both methods are almost direct one-for-one copies of those methods we employed in the DC circuit analysis of resistors. However, one needs to take into account two additional rules when dealing with complex impedances. First, one needs to calculate the complex impedance of elements comprising the parallel relationship at that specific frequency. And second, one must take into account the angle of those complex impedances comprising the parallel relationship during the calculation process. Long story short, direction matters, and if you forget this fact, you will fail. Using the quick and dirty method to solve for the total impedance of two parallel elements necessitates a user multiply Z1 and Z2 and then divide this product by the sum of Z1 plus Z2. Note the summation of Z1 and Z2 is entirely below the division operator and may necessitate the use of parentheses if you perform this calculation in one entry on the scientific calculator. The more involved method to solve for the total impedance of two or more parallel elements necessitates a user add the inverses of those elements comprising the relationship and then take the inverse of this sum. 1 over Zt equals 1 over Z1 plus 1 over Z2 plus 1 over Z3, and so on. Importantly, you must realize that this method solves for 1 over Zt, not the total impedance Zt. One must take the inverse of 1 over Zt to obtain the final total impedance Zt. Allow me to demonstrate the use of these methods with a couple of illustrated example problems. Consider the parallel or side-by-side relationship of a 200 ohm resistor and a 530.5 millihenry inductor subjected to sinusoidal AC voltage with a frequency of 60 Hz. We need to convert these individual components to complex impedances and then calculate the total impedance using one of our two available methods. Because this is an arrangement of only two elements, the logical choice of methods is the quick and dirty method. The 200 ohm resistor is a complex impedance of 200 ohms at an angle of 0. You don't need a formula to calculate resistive complex impedance. All you do is take the resistance value and stick at an angle of 0 degrees behind it and call it good. Illustrated on the impedance diagram, the resistor has a magnitude of 200 ohms and is pointed entirely in the real horizontal positive x direction. The inductor necessitates a slightly more involved calculation. The impedance of an inductor is 2 pi FL at an angle of positive 90 degrees. Substituting our given values into the equation, we arrive at an inductive impedance of 200 ohms at an angle of positive 90 degrees. Illustrated on the impedance diagram, the inductor has a magnitude of 200 ohms and is pointed entirely in the imaginary vertical positive y direction. Before we perform the total impedance calculation for this parallel relationship, let's take a look at these individual components. Both our elements have a magnitude of 200 ohms. Does this mean the 200 ohm resistor is functionally equivalent to the 530.5 millihenry inductor at 60 Hz? Absolutely not. They are entirely different entities, and the impedance diagram clearly illustrates they are pointed in two totally different directions. Again, you must take direction into account, and the moment you forget to take direction into account is the moment you fail. Using the quick and dirty calculation method, we arrive at a total complex impedance value of 141.4 ohms at an angle of 45 degrees. Note the total impedance magnitude of this parallel arrangement is less than either element's magnitude. This is to be expected given parallel arrangements are side-by-side paths, allowing more opportunities for current to flow. Additionally, note the positive 45-degree angle indicates ZT, the total impedance of this parallel relationship, appears to be a mix of both the resistive and inductive nature of these two elements. This is to be expected given the equal magnitudes of the resistive and inductive components comprising this relationship. This balanced condition, however, is only true at 60 Hz. Consider if we dropped excitation frequency in half to only 30 Hz. The resistor is essentially immune to frequency effects, and as such remains a complex impedance of 200 ohms at an angle of 0. The inductor, being a reactive element, however, must take into account this reduction in frequency. Substituting our given values into the equation, we arrive at an inductive impedance of 100 ohms at an angle of positive 90 degrees. Illustrated on the impedance diagram, the inductor is still pointed entirely in the imaginary vertical positive y direction, only its magnitude has been cut in half. Using the quick and dirty calculation method for this new condition at a decreased frequency of 30 Hz, we arrive at a total impedance value of 89.4 ohms at an angle of positive 63.4 degrees. Note the total impedance magnitude of this parallel arrangement is less than either element's magnitude and less than our original calculation at 60 Hz. This is to be expected given one element comprising the parallel relationship has decreased in magnitude and parallel arrangements are side-by-side paths, allowing more opportunities for current to flow. Additionally, note the positive 63.4 degree angle indicates ZT, the total impedance of this parallel relationship, appears to be favoring the inductive end of the spectrum. This is to be expected given the inductor's magnitude is half that of the resistor and more current would be expected to flow through it. The element in the parallel relationship with the lowest magnitude seems to be determining the nature of the total impedance. This condition, however, is only true at 30 Hz. Consider if we raised excitation frequency to 120 Hz, twice the initial value. As previously, the resistor is essentially immune to frequency effects, and as such remains an impedance of 200 ohms at an angle of 0. The inductor, being a reactive element, however, must take into account this increase in frequency. Substituting our given values into the equation, we arrive at an inductive impedance of 400 ohms at an angle of positive 90 degrees. Illustrated on the impedance diagram, the inductor is still pointed entirely in the imaginary vertical positive y direction, only its magnitude is twice our initial calculation. Using the quick and dirty calculation method for this new condition at an increased frequency of 120 Hz, we arrive at a total impedance value of 178.9 ohms at an angle of positive 26.6 degrees. Note the total impedance magnitude of this parallel arrangement is still less than either element's magnitude, however it's larger than our original calculation at 60 Hz. This is to be expected given one element comprising the original relationship has increased in magnitude. Additionally, note the positive 26.6 degree angle indicates ZT, the total impedance of this parallel relationship, appears to now be favoring the resistive end of the spectrum. This is to be expected given the inductor's magnitude is now twice that of the resistor, and less current would be expected to flow through it. Again, the element in the parallel relationship with the lowest magnitude seems to be determining the nature of the total impedance. These three scenarios are meant to illustrate an important fact when dealing with parallel or side-by-side relationships of complex impedances. The resultant total impedance of a parallel relationship will always be a mixture of those elements comprising it, favoring the smallest element's contribution. This is essentially opposite to what we observed in series circuit relationships, where the resultant total impedance of a series relationship is always a mixture of those elements comprising it, only it favors the largest element's contribution. Again, for parallel relationships, the resultant total impedance of a parallel relationship will always be a mixture of those elements comprising it, favoring the smaller element's contribution. Recall when the resistor and inductor had equal magnitudes at 60 Hz, the total impedance of the parallel relationship appeared to be an equal mix of the two. If, however, the inductor is smaller at 30 Hz, the total impedance of the parallel relationship appears to be favoring the inductive end of the spectrum. Finally, if the resistor is smaller at 120 Hz, the total impedance of the parallel relationship appeared to be favoring the resistive end of the spectrum. In summary, the element with the smallest impedance magnitude largely determines the nature of the resulting parallel complex impedance. This again is essentially the opposite of what we observe for series circuits. However, it's totally keeping with those expectations we established in the DC analysis of parallel arrangements of resistors. Parallel arrangements are side-by-side paths allowing increased opportunities for current to flow. The path with the least impedance would wield the most influence on both the magnitude and direction. This being said, capacitors and inductors are essentially mirror images of one another, and as such can moderate each other's influences. Allow me to demonstrate. Consider another parallel or side-by-side relationship of a 160 ohm resistor, a 180 millihenry inductor, and a 27 microfarad capacitor, this time at an excitation frequency of 50 Hz. We're being asked to solve for the total impedance of this parallel circuit comprised of 3 elements. The logical choice of techniques is the more involved calculation method for 2 or more elements in parallel. The 160 ohm resistor is an impedance of 160 ohms at an angle of 0 degrees. The inductor and capacitor necessitate slightly more involved calculations. The impedance of the inductor is 2 pi FL at an angle of positive 90 degrees. Substituting our given values into the equation, we arrive at an inductive impedance of roughly 56.5 ohms at an angle of positive 90 degrees. The impedance of the capacitor is 1 over 2 pi FC at an angle of negative 90 degrees. Substituting our given values into the equation, we arrive at a capacitive impedance of roughly 117.9 ohms at an angle of negative 90 degrees. When we add 1 over ZR plus 1 over ZL plus 1 over ZC, we arrive at 1 over ZT being equal to 0.011 at an angle of negative 55.8 degrees. Taking the inverse of 1 over ZT, we arrive at ZT, the total impedance, being equal to 89.9 ohms at an angle of 55.8 degrees. ZT, the total impedance of this parallel relationship, appears to be primarily inductive given it's in the first quadrant. This is to be expected given the inductor is the element with the smallest magnitude and is the path through which the largest amount of current would flow. This being said, the capacitor in parallel seems to be moderating its influence. This condition, however, is only true at our given excitation frequency of 50 Hz. Consider what would happen if we raised excitation frequency to 400 Hz. Which reactive element's nature would now dominate this circuit at this dramatically increased frequency? You should be able to predict this effect with a simple mental exercise. Given resistors are essentially immune to the effects of frequency, we could expect its contribution to remain unchanged. The magnitude of the inductive complex impedance, however, is directly proportional to excitation frequency, and we should expect its magnitude to increase. The magnitude of the capacitive complex impedance, in contrast, is inversely proportional to excitation frequency, and as such we should expect its magnitude to decrease. Given the element with the smallest magnitude would dictate the nature of this parallel relationship, we should expect the capacitor to steal the show at 400 Hz. Let's prove this hypothesis with some calculations. At 400 Hz, the 160 ohm resistor would still present a complex impedance of 160 ohms at an angle of 0 degrees. Substituting our given values into the inductive and capacitive complex impedance formulas, we arrive at the following results. The inductor has a complex impedance of roughly 452.4 ohms at an angle of positive 90 degrees. As we expected, its magnitude increased. The capacitor has a complex impedance of roughly 14.7 ohms at an angle of negative 90 degrees. As we expected, its magnitude decreased. When we add 1 over ZR plus 1 over ZL plus 1 over ZC, we solve for 1 over ZT. Taking the inverse of 1 over ZT, we arrive at ZT being equal to 15.2 ohms at an angle of negative 84.6 degrees. ZT, the total impedance of this parallel relationship, does indeed to be primarily capacitive, given it's deep in the fourth quadrant. This is to be expected, given the capacitor is the element with the smallest magnitude, and it is the path through which the largest amount of current will flow.